So to introduce you to the full adder, we're going to represent it in a slightly different way, where we're going to treat it like it's a black box. So we've got A input, B input, and we've got this brand new input, which is called CI, or another way of saying it would be the carry in. And you're like, probably what? Well, let me explain. All of these aspects are going towards our big black box called full adder. End result, two outputs. Now let's imagine that this full adder is a part of a larger circuit where there's other adders beforehand passing on data. What CI would be the previously carried in bit from the previous half adder. So it'll be from the previous half adder. For example, it'll be passing on its carry to this sum, so we can carry it on in our calculations, where we've got S and we've got CO, which is a carry bit like the half adder would be, and the sum like the half adder would have. So the difference is a half adder won't be able to include any carry bits from a calculation moving forward, whereas a full adder allows us to use these carries in our calculation. So if we were going to do a binary addition, let's do one down here in the corner. Let's do 1 1 0 1 1 plus 1 0 0 0 1. We would have 1 add 1, which gives us a 0, and what we're going to do is we're going to carry but 1. Now obviously we need to carry this into an adder to do our addition, but you can see now we're dealing with 3 bits rather than just 2, because we're using this carry in bit from this calculation here. A half adder wouldn't have allowed us to do this. A full adder is allowing us to do this, and that is the difference in terms of them being used. So what does this look like as a truth table to start off with? So let's have a look at the truth table. It's not a coincidence that when we've got a 1 for sum, we happen to have an odd number of 1s in our input. So let me just make this a bit thicker. There's a 1 there, there's another 1 there, and it's odd. We can see that. Here, there's an odd number of 1s in our input, leading to 1 being our sum. And the same with this one. 1, 2, 3, and sum there. There's another pattern. Carry is 1 if we have 2 or more inputs being 1. So we can count 1, 2 inputs here being 1, so therefore carry is 1. We have here 1, 2, which means that carry is going to be 1. 1, 2, carry is going to be 1. 1, 2, 3, which is higher than 2, obviously. So carry is also 1 here. So that's 2 rules. 1 for carry, 1 for sum. Sum, it needs to have an odd number of 1s, whilst carry needs to have greater than 1 number of 1s, i.e. 2 or more. And if I was going to basically use a k-map to actually turn this into an expression, what you would find out would be the following. When we have our carry out, i.e. our carry here, it is using the following. We have A and B, or B, C, in, so I for in, or A, C, in. For sum, we could have an A, nor, B, nor, C input. So basically inside this black box, is a combination of these different gates. Let's have a look of an actual example. So if we're going to do this as a circuit, what we're going to do is, if I just draw it here, we can have A, B, and C carried in. And the first gate we're going to have is the NOR. I just want to make a very quick correction to what I've just said about these. These are ZORs. And I think I call them NOR. That's my fault completely. Pretty tired at the moment. So if we go to a circuit based on this, we're going to do the ZOR gate. So let's do a big one there. Really badly drawn circuit. And that would be sum. Now remember, CI is a carry from potentially a previous adder. As I said, I'm pretty tired. So yeah, CI could well be a carry from a previous adder. So if we're going to now draw the circuit for the carry, what we would have, I'm going to do this really small up here, is AB, B, C, I for carrying, and A to draw that. And A and B are connected by an AND. B's are connected by an AND. These are connected by an AND. And it goes into a 3 input OR. So before we go into some exam questions, etc. to do with this, it's good to see how this all fits into the big picture. So what we have here is a combination of full adders and a half adder. And we're starting over here where we've got A and B. So it could be like 1, oops, daisy. It could be like a 1, yo, that's so big. Let's undo that. Let's try that again. It could be a 1, it could be a 0, whatever. Now you get your sum coming out here, and if there's a carry, it could be either a 0 if there's nothing to carry over, or it could be a 1. That carry will then go towards the next. But this time we have to use a full adder because that carry means we've got a 3 input. So that is the purpose of why we've got the full adder, as I said right at the beginning of the video. So the carry will keep going on and on and on until there's no more need for that. The calculation has been done. So all these adders are taking place, as you can see, to work out. We've got 1, 2, 3, 4, 5, 6, 7, 8. So no doubt to work out an 8-bit calculation of some sort. Let's have a look at some exam questions. So I want you to have a look at this question. And before you move forward with it, I would like you to pause it, give it a go, and then I'm going to show you a solution to the video. So, pause the video. Good luck. Okay. So, I think the easiest thing to do would be to identify what J is and what K is to begin with. So, if you remember earlier in my video, I said to you that the carry would be the OR gate. And I swear to you that I can't use this still. There we go. Carry. And let's make that a bit bigger. Which means that K is going to be sum, which should be the ZOR. That's a really bad ZOR gate. Now, if you remember when we went through that truth table, I gave you some rules to remember about the inputs. So I'm hoping you remember that 0 will be 0. 0, 0, 1, we've got odd. Therefore, the carry will be 0, but the sum will be 1. The same with this one. Now, in order for the sum to be a 1, it needs to be odd. In order for the carry to be 1, it needs to be greater than 1. So we've got 1, 2. It gives us an even number. However, it's going to be 0 because it's odd number, but a 1 here. This is going to be a 0, 1. This 1, 2, 1, 2, 1, 2, 3. So we've just done a truth table for a full adder. And there we go. We can also tell it's a full adder because we've got 3 inputs.